I'm going to talk about S3 file systems today and trade-offs. And if the photo here gives you any impression, fitting a square peg into a round hole involves some difficult choices. And I hope I can kind of inform you about how you can choose between the many options available. I did hear that there are some issues with fuzzy slides or low resolution slides. And so these are all available at gaul.org/talks. A little bit about me. I contributed to a number of different free software file systems, network-based file systems. So I'm a committer to S3FS, one of the three systems we'll talk about today. And I've contributed a little bit to Goofy's kind of a comparison point we'll talk about later. I've done a bunch of cross-cloud things as well. For Apache JClouds, it's a Java-based multi-cloud toolkit. And then I wrote kind of interesting or sometimes useful testing tool called S3 Proxy, which lets you interoperate with any object store via the S3 protocol and do some testing and that sort of thing. I do live in Tokyo, so if you see me swigging on my coffee during this, I'm trying to fight off the early morning here. There's a couple ways to get in touch with me. If you are a civilized person, there's some old school ways on my website. Otherwise, you can talk to me in an uncivilized way on Twitter. Okay, so let's define what we're talking about here. So what is an S3 file system? So usually people want to use these when they need some degree of Posix or Linux application compatibility. Oftentimes people are actually using a native S3 application, maybe Hadoop or something else, and S3FS or some other S3 file system as well to get multiple views into the same data. People will often do kind of maintenance work or something with a S3 file system, and their main application is using S3 protocol directly. And the reason you use S3 specifically is it tends to break down into two use cases. Sometimes people are storing lots of data. They think about terabytes or even petabytes of data. And this is one of the cheapest ways to do it while retaining good performance. And the reason it's cheaper is because S3 tends to be a distributed system. There's many different implementations of S3 that we'll talk about in a moment. But some of them, it can just kind of scale out and you keep adding nodes. And so it's easy to expand that and store lots of data. Those workloads tend to be kind of like archival or analytics. Machine learning is kind of a new one. And the second use case that is more relevant to me and maybe many of the audience here is as a kind of a lightweight network file system. So I use it on my laptop to store bulk data that doesn't fit onto my SSD. There's also a wide variety of Raspberry Pi users who have a similar problem with their tiny compact flash. So they want to store data on a bigger device. So the kind of thesis of this talk is that there are trade-offs involved in the systems I'll present, and you can't have everything you want. You can't have Posix or Linux compatibility. You can't have a native object access where other applications that don't use that file system can access it. And you can't have speed. So it's a classic kind of engineering trade-off. Pick two. So just to give some background on what we're talking about, these S3 file systems are written in Fuse, written on top of Fuse, rather. And so they're actually not in the kernel like ext4 or XFS or traditional file system. These are user space programs that you can run and kill and kill -9 or whatever you want, debug with GDB, which kind of allows maybe a little more complexity and things that you might not normally do in the kernel. And so the Fuse itself, it takes these system calls, and so the system call, it just takes a buffer and kind of emits it to a file descriptor is a pretty good example of this. And there's a pretty one-to-one mapping of these system calls to Fuse operations, some extra metadata that's not important here. Fuse is very mature. It's been around for over 10 years. There's a ton of different kinds of file systems, not just S3. There's a BitTorrent file system, which is kind of fun. There's a Dropbox file system to get a view into Dropbox's service. SSHFS is probably the most popular one that people are familiar with, where you can take a remote machine and mount any path of its via SSH. It has some overlapping use cases with some of the S3 file systems. There are literally hundreds of these things. They do almost everything. Hundreds might be a low estimate. So what is S3? So this was introduced by Amazon, who coined the simple storage service name. And this is, there's two ways to look at this. There's an implementation that Amazon provides, and there's also kind of the protocol itself that has been re-implemented many times. And it's a pretty simple protocol. I have implemented it in S3 proxy. It's a little bit XML heavy, but it's pretty narrow, and it's easy to implement. So again, object storage offers kind of scale out or kind of fast performance while retaining low cost compared to other kind of network, traditional network file systems like NFS. There are many implementations. There's the kind of hosted ones, Amazon, Backblaze, and Google Cloud Storage. But there's also a number of free software ones, Ceph, Minio, and OpenStack Swift. So you really can kind of bring your application to whatever backend that you want. And this is a really mature ecosystem. There's a lot of applications now have native S3 compatibility, and there's a bunch of SDKs for every language. I just want to give an example of what S3 looks like. It's not magic. It's just HTTP underneath. You can put a key into a bucket. This is going to create an object. In this case, it's only 14 bytes saying hello world. Kind of the important thing here is that there's these x-amz-meta. This is where metadata is stored. It's how some of the upcoming file systems store things like mode bits or permissions, owners information, that sort of thing. There is a separate set of permissions, the XAMZ ACL, that is public or private read. Sometimes this gets a little bit confusing having two layers of ACLs. One of the two systems is enforcing. So let's just look at what the difference between Posix or the Linux APIs and the S3 APIs look like. So there's some similarities here where you can think of the read system call mapping onto to get object. Write kind of maps onto put object, and unlink, delete. Reader is, we'll explore reader later, but it's kind of incomplete from, or list object is incomplete from the reader point of view. But there's a bunch of operations that are different. So you can't rename things in S3. You can copy them and then delete an object, but that's not atomic, and it doesn't work on directories because there's no notion of directories in S3. Similarly, you can't change mod an object, but you can copy an object to itself, which is pretty expensive, but it's a server-side copy, so the user mode program doesn't see it. But the important thing is you lack some system calls, specifically open and lseek. This is because Posix is stateful, where you can open a file and then interact with that file descriptor. But S3 only works on the key or the path. And so there's no notion of like seeking to an offset. You could just read at that particular offset. But let's say if you were to unlink a file, I guess read continues to work. But so there's a tension here between the system calls that exist and the ones that don't, and the ones that are kind of different that we'll explore in the next couple slides. So let me introduce S3FS. This is the one I'm most familiar with. I am not the creator of this. I joined much later. There have been several different maintainers, but it's one of the earliest S3 file systems. It's probably came out in 2007, I want to say. And so it had a focus on native S3 object interoperability. And to define that again, that's, you can access the same objects through S3FS as you could from any other S3 application, including the AWS CLI or rclone or Hadoop or something like that. And the second focus is on Posix compatibility. So it tries to give the highest fidelity Posix implementation that it can, given that it wants to access the objects, keep the files in the native S3 object format. So this means that there's no atomic renames. Again, there's no S3 rename API. There's only copy and delete. And you can't really implement hard links either. There's not a concept like that in S3. But most of everything else works. All the C time and read write, everything works the way you'd expect. And this does allow you to mount a bucket with multiple clients can mount simultaneously. Although there's a bunch of caches in S3FS that we'll talk about in a couple slides that may give you unexpected results. This is not like NFS where there's a delegation, that there's a strong semantics about what happens when two clients modify something at the same time. S3FS is very complicated. It has tons of configuration knobs, probably too many, that allow you to trade off performance for other considerations. There's a lot of backward compatibility things you can turn on and off as well. We are trying to rationalize that, but it's still really complicated. Chances are you can just apt-get install this on your distribution of choice. It exists almost everywhere. Debian, Red Hat, Ubuntu, FreeBSD, even Mac OS. We're trying to get this on Windows, but there's not a lot of free software Windows hackers for obvious reasons. The usage of S3FS is pretty simple. Again, this is a user mode program, so you just run the S3FS binary, and you take the bucket and give it a mount path. And then you can interact with that path as if it's a local file system. So for example, you can echo foo into mount/foo, and then you can retrieve that file, and it says foo. Similarly, all the metadata exists here when you do an ls-l. And you can actually kind of round trip this through the AWS CLI. And so this is just the tool that Amazon provides for interacting with buckets. And here the commands sound similar, but it's really issuing the get object and list objects and that kind of thing. Let me just talk about read. This is where S3FS actually does pretty well. The performance is good. So when an application asks for a data at a given offset, maybe at 128 kilobytes, S3FS will issue a bunch of parallel requests and trying to grab as much data as possible and stuff it into a cache. So after it gets all that data, it will return the amount that the user requested. And then it'll cache that data for the future reads. And so performance is actually really good here, mostly because of caching. And so when users are doing read-heavy workloads, they tend to be pretty happy. But as we'll explore in some slides, not everything is so easy. So S3FS writing, when you just create a new file, performance is actually pretty good as well. So when an application calls write, S3FS doesn't write that to S3. It actually writes it to the local disk and kind of spools it there. And then when a couple different conditions happen, when the file is closed or the user f-syncs it, or when more than a configurable amount of data is written, it will actually kick off that process to synchronize that and block the close call, for example. And so we don't need to think about this too much, except that there's a multi-part process to upload data. You say, I want to create an object. I want to create a large object. And then you say, upload these parts of data, and then issue a complete multi-part upload saying this is now complete and expose this object to the system. Performance is pretty good here. Writing to local disk does have its drawbacks. People who create very large files tend to be concerned about how much local space they're using, but performance is good. So writing to an existing file is not so good. And so people who are trying to run some database or something, usually, or some other kind of mutating process, are not very happy with S3FS and probably should not be using this because there's just a complicated process here. I don't know how much detail I'm going to get into, but for the data that doesn't exist locally, it has to do kind of a read, modify, write to satisfy a minimum object size condition of S3. Then it can kick off the multi-part process we talked about earlier. The important thing here is that it will use a server-side copy for the unmodified data. And so that's pretty good from S3FS's point of view, but it's actually doing a lot of work on the S3 side. So if you were to write a 1 byte sequence maybe to the end of a file, it turns into at least 3 RPCs, and it will do 4 RPCs, and will do like big O of file size server-side I/O. So that's pretty expensive and pretty bad. It really can't be helped though, given the conditions that, given the restrictions that S3 imposes on us. And the last example from S3FS is actually even worse. So this is a user's first experience. Oftentimes they try to list a bucket that has many objects in it. S3FS will call the obvious list objects RPC. List objects return some basic information, like the file name, the size, the modified time. But to get the full Posix richness, S3FS needs to issue a bunch of head objects. And so this will get extended information, permissions, owner, so A time, Z time. So this is actually really terrible. So if you have 1,000 files in your directory, it will do 1,000 RPCs. This really can't be avoided when we want to give the full compatibility of Posix. And so there is a solution to this. S3FS does cache many things. This can address a lot of the performance issues that users have. There are 3 caches. The stack cache is probably the most important one. It holds the file metadata that the kind of ls-l information that you're used to. Caches 100,000 entries by default. Holds on to those for 15 minutes. That means that your data can be stale for 15 minutes if someone else, maybe another S3FS process, updates it. There are some other caches that are not on by default. Some for legacy reasons, some for kind of user experience. The no object cache is kind of a negative cache, where surprisingly common operation that applications do is they check for the presence of objects that don't exist. And so enabling that will help a lot of build workloads and that sort of thing. The data cache, S3FS does cache a certain amount of data, but you can instruct it to cache more. It's a configurable amount. What's kind of surprising to users is that the write cache and read cache are separate things. The temporary space is not considered a cache, and when you write a file, it doesn't have it doesn't keep that in the read cache as well. So it's kind of a flaw in the S3FS. Only one of these is enabled by default. So S3FS is a very complicated system. So a colleague of mine wrote something called Goofies, which is similar to S3FS, but has kind of stronger opinions about what a file system should do. So this has a focus on performance, and specifically on large files that are often found in more analytics and kind of machine learning workloads. It's a very simple mapping from POSIX to S3. It doesn't try to do things that are very complicated, these heroic multi-RPC operations. And so it doesn't support even more of POSIX than S3FS. Atomic renames or hard links like S3FS it doesn't support. But it also doesn't support random writes, which tends to be important to some people. Kind of an easy way to think about this is that you can create a tar file with Goofies, but you can't create a zip file because of the way zip files are created. It has a table of contents in the beginning of it that is mutable, and Goofies cannot support that. Similarly, fsync is not supported. If you want to sync the file, you just write and close it. Goofies, it doesn't make the guarantees about fsync that other file systems do. It has to fake some of the metadata to achieve its performance. So it doesn't have some of the things we talked about earlier about UIDs, GIDs, permissions, and some of the timings. It does support mtime because S3 gives you that for free. It doesn't have the aggressive caches that S3FS does. It does have an external companion file system called catfs that you kind of stack on there and provide some amount of caching. But Goofies tends to be a lot easier to use because it doesn't have the legacy that S3FS says it was created. More recently, it doesn't support some of the old school S3 pseudo directories and stuff like that. It doesn't have so many knobs to tune things. Its opinion is that Goofies will make the right choice for you, and oftentimes it does have better defaults out of box. But when it doesn't, you can't tune it as much, which does upset some users. I'd just like to walk through a couple examples of where Goofies shines. So you can just compare these. The smaller bars are better in these graphs, but writing tends to be twice as fast for Goofies. It's avoiding the spooling to disk specifically. And it has twice as good create performance for reasons that are kind of strange within S3FS. It actually, when you create a file in S3FS, it creates a 0-byte object with all the metadata, and then it'll overwrite that. So it's doing twice as much work as Goofies in this case. And so this is unfortunately hard to see because it's only listing 1,000 files. But you can see that to list 1,000 files in S3FS might take 1,000, one second to list 1,000 files, where it takes maybe 200 milliseconds for Goofies. These tests were performed on a LAN, not over like the internet with 100 milliseconds latency. So you you may be more disappointed with the listing performance if you're running remotely. Let's walk through some of the examples here where performance differs. For writing, again, Goofies has a better writing performance. It doesn't spool to disk. It actually just buffers parts in memory. And it's actually a little more clever than that, because as soon as it receives a certain amount of data, it immediately flushes that to S3. And so it can asynchronously upload while the user is continuing to append to the file. And when it calls close, it'll issue that last upload part, and it'll issue a complete multiplier upload completed. But almost all the work was already done before the user called close. Versus in S3FS, it does all the work at close or at fsync. And so performance is actually really great here, especially with larger files, and it's usually just network limited. You're really running at line speed. Similarly, readdir is also a good example. So when the application calls readdir or get durance, Goofies just issues list objects. It gets the basic information, and it returns the basic information. It doesn't interrogate each object to get the permissions or that sort of thing. And so this is really good performance. And so the reason that Goofies can kind of get away with this is that S3 has its own permission structure. And so users are usually more interested in that. Not always, but usually. And so some of these extended metadata just aren't important to some users. Modified time tends to be more important than access time, for example. Access time is kind of a troublesome one to implement for users, for file system implementers. But a single system call only issues a single HTTP request. So this is good. And I'd like to talk about the last of the three file systems, S3QL. And this is the most different from the two before. And so this one has a different set of focuses, first on performance and on Posix compatibility. And it gives up native object access. So objects created via S3QL, or files created via S3QL, cannot be read by the Amazon CLI or Hadoop or something like that. It has very fast metadata access because it stores the entire file system view in a local SQLite database. For durability reasons, it syncs that to S3 every day, but it can service all of those locally. And so its philosophy is quite different here, where it treats the object store like a block device, like a traditional hard drive. Its hard drive notion in the sense is ones with 10 megabyte sectors, but it's like an opaque format, just like let's say the ext format is opaque to exitfs, right? You can't read, can't use exitfs to read ext4 data and vice versa. So because it has made these choices, it actually supports the entire range of Posix, including atomic renames and hard links. Because it controls the data format, it has kind of what we think of as advanced file system features that you normally would get from like Btrfs, where you can deduplicate data or do snapshots so you can go back in time. Does have some drawbacks. Only one client can mount a bucket at a time, so there's not really a sharing. If you want to share data that's stored in S3QL, you need to run maybe NFS or something on top of S3QL or Samba or something like that. The usage is a little bit different than S3FS or Goofies because you actually have to make a file system. You can't use existing objects, so you just call them makefs.s3ql. Here I'm not using encryption and turning off all the debug output. But when you mount the bucket and you use an external tool to introspect on the bucket, you see that S3QL is putting its own metadata in there. And so when you create a file via echo and then unmount it so that it flushes, you can look via AWS S3 LS, and you can see that it wrote not just the 4 bytes into a file named foo, it actually stuffed them into an opaque object called S3QL data 1. And so your data foo is stored in that thing, but in that object, but it's not accessible to other programs. There are some other metadata in here that aren't particularly relevant, except that the metadata is a SQLite database. Let's look at the two operations from before. So when S3QL writes a file, S3QL writes it to the, sorry, when application writes a file, S3QL loads it to the local disk. And then when the application closes or fsyncs, S3QL can asynchronously write that to S3. So it can actually write it after the close. And so performance is actually great here, at least for small files where you're not network limited. For very large files, if you're trying to write a couple terabytes, you would actually prefer the Goofy's approach, which is just streaming data. But usually for maybe a lightweight network file system use case, this is really a great way to write data. Reader doesn't require any RPCs. S3QL can satisfy that locally from the just from its database. So I want to go back to the trade-offs we talked about earlier. And so we can kind of see that the three systems map onto two of the three properties, and there's nothing that can sit in the middle of the three and satisfy everything. So really, it depends on your use case about which system you should prefer. There's a little more detail about the interoperability and compatibility. So we can kind of compare them here. And the two interesting examples here are Goofy's versus S3QL. And you can kind of see the things that one supports are not supported by the other. So native object access and multiple buckets, multiple clients mounting a bucket are supported by Goofy's, not supported by S3QL. And kind of the extended Posix operations are not supported by Goofy's. And you can see how S3FS kind of straddles that and tries to offer both. And that kind of explains why it has slower performance. Similarly, we can look at the performance here, and we can go from right to left. S3QL doesn't need to do RPCs for most of its operations, where it can delay them until after when it's doing right behind flushing. Goofy's doesn't need as many RPCs and can stream uploads, which is a good feature. But S3FS to support for its trade-offs, it has to do a lot more RPCs, and specifically readdir is pretty bad. Writing to an existing file requires a server-side copy. This tends to be disappointing, especially if you're not local. If let's say your object store is far away. Just to conclude here, so before you choose a file system, just consider the trade-offs that your application can tolerate. Do you want something that's faster, or do you want something that's more compatible, or do you need to interoperate? And so each one of these can address some of the use cases, and hopefully some of yours. And just like a warning here, please use a native S3 application when available. Don't use, for example, S3FS and rsync on top of it. There are replacements like rclone, or even the AWS CLI can do a rsync-like operation. And so don't use a file system if you don't have to, would be my advice. And so I don't know if we have any questions. Don't see anything.
Yeah, we do have a couple of questions, Andrew.
Okay.
In QA window.
Sorry, I don't see them in Zoom.
Not in Zoom, in the Zoom QA window. So if you go on bottom side.
Okay. New projects, the best ones to use Phosphorus. I think that's from before. Is there an API ref like Swagger UI or something for these requests? Yes. So there's Amazon has a REST API documentation that is pretty good. The API is relatively small, so I'd recommend just going to Amazon for that. There are some undocumented APIs that I have a GitHub repository that documents that there's some extended operations that maybe Ceph supports that Amazon doesn't support, or sometimes vice versa. Amazon has some undocumented APIs that exist to get some more richness out of the system. And so if you go to github.com/Gaul, you can find those. And the second question is, are user space file systems like this suitable for production interfaces to S3? Is this more for manual intervention with S3 stores in a local context? People use S3 file systems in production, definitely. I see the bug reports. I think that your mileage may vary with these. Certainly, some LTS distributions have older versions of S3FS, for example. And so there are bugs in Ubuntu 16.04 that are long fixed that people show up with bug reports for. I strongly discourage using very old versions of S3FS. The new versions fix a lot of performance and even data loss issues. So if you're using LTS distribution, I would recommend compiling from source. But the Ubuntu 20.04 is good. All the Red Hat enterprise packages are good. They're the latest packages. The next question is, are other cloud file system solutions generally using the S3 file system, or is this unique to Amazon? I'm sorry, Jared wants to ask this live. I don't understand that piece of metadata there. So these aren't specific to Amazon. There's many different S3 implementations, including ones from Google and Backblaze. And then there's a bunch of free software implementations like OpenStack Swift or Minio that you can run yourself. So I would not say this is unique to Amazon in any way.
Very good. So I guess that's it as far as QA is concerned. Once again, Andrew, thank you so much for waking up early. What is time in Tokyo, by the way, right now? Is it like 7 a.m. or something?
7 a.m. I did wake up at 5 a.m. Well, thank you. And here's the slides again. And I will be available the rest of the day on a chat and hopefully during the game night.
Very good. Well, the good thing is that it's Saturday for you now, so you don't have to go anywhere or do work or something. Awesome. Once again, thank you so much,